Cool. Hi, everybody. I'm Zach, and I'm the CTO of AZTEC, and I'm here to talk about our protocol, which is a privacy solution for Ethereum. So before I dive into it, just a brief overview. I want to talk about kind of what is AZTEC, how do we provide privacy for Ethereum, how do we make it so that you can send value confidentially. And also go through some of the kind of what we view as some of the problems with privacy solutions on Ethereum, inherent in privacy solutions on Ethereum, and what we can do to solve them, and then go into what we've done. So private transactions on Ethereum present a bit of a problem. How can you enjoy the consensus benefits you get from a blockchain without having, whilst also being able to transact private data? And do so in a way where you don't need some kind of privileged actor or entity that has the ability to kind of decode this data and identify what's true or false. How can you give that power to anybody observing that blockchain? It sounds like a bit of a contradiction in terms, but it can be done through an extremely obscure branch of mathematics called zero-knowledge cryptography. A lot of zero-knowledge proving systems have cropped up recently that aim to solve this problem. So there's snarks, bulletproofs, like homomorphic encryption, the AZTEC protocol. But there is an enormous problem with zero-knowledge cryptography. In my opinion, it's kind of almost become a bit of a shibboleth in the Ethereum community, like this idea that zero-knowledge proofs are going to solve all the problems. They're going to solve scalability, they're going to solve privacy, it's going to solve everything for us. But if you the truth is a little bit far away from the reality is a bit far away from the vision, because zero-knowledge proving systems are extraordinarily difficult, fiddly to work. They present a massive user UX challenge. You don't want to have your clients having to spend seconds or minutes, constructing zero-knowledge proofs. You don't want to have your clients deal with commitment functions and encryption schemes and a plethora of all the problems that come with that. And they're also incredibly inefficient. So how do we bridge the gap between the vision and reality? How do we bring zero-knowledge proving systems to Ethereum in a way which is accessible and workable? So in my opinion, these are the building blocks of a confidential ecosystem that are required for zero-knowledge proving systems to become useful, for privacy solutions to become actually workable and adopted by the mainstream. And that is, you need some kind of method of confidential transaction semantics that is customizable. One of the great strengths of Ethereum is the fact that it is a Turing-complete blockchain, which means and by that I mean the blockchain designers didn't expressly define what you could do with that blockchain. They understood that they didn't really know what people wanted, and that they gave developers the tools for developers themselves to decide how they could add value into a blockchain ecosystem through the smart contract platform. And I think that any kind of confidential transaction system has to have that same flexibility. That you can't just say, here is how you here is this one method you can use to transfer confidential value, and you can't have any edge cases, you can't have any extra logic, you can't have any customizable semantics, because then that's not really very useful in the real world. You also need confidential cross-asset interoperability, which I don't think is something that's really talked about very often in the context of zero-knowledge proving systems. It is one thing to be able to define a single confidential kind of digital asset or cryptocurrency that you can trade and transfer around without anybody knowing what's going on, inside. But the use cases of that are somewhat restricted. Where the value is by enabling Ethereum to become a confidential settlements layer through trades of different confidential assets, and those trades happening and settling in a confidential manner. And in order for that to happen, private digital assets have to be able to be interoperable, they have to be able to talk to one another, which is traditionally quite hard in a zero-knowledge proving system. In addition to that, you need a lot of more developer-friendly tooling than exists today. Right now, working with zero-knowledge cryptography on a blockchain platform is extraordinarily difficult. I mean, the reason why I developed AZTEC was because I originally came up to this problem because I was building a syndicated loan platform on Ethereum, and I needed privacy, and I couldn't get privacy. And in order to get privacy, I had to develop this and kind of become quite literate in zero-knowledge cryptography, which is obviously not sustainable for a mature ecosystem. We need to provide high-quality tools that mean that developers who don't have any kind of knowledge of zero-knowledge cryptography can still use these tools, understand how they're used, and have it have them be easy to use, in the same way that we can all construct Ethereum transactions and send them to an Ethereum network without having to understand the precise mathematical mechanics of an ECDSA signature. And the final thing is extremely important, is efficient proof construction and verification. It's all a bit meaningless if your proof takes an hour to construct and requires a terabyte of RAM. It's not very workable if the verification of these zero-knowledge proving systems takes an inordinately long time, because it means that every single validator node that's running has to also then validate that proof, and that massively constrains your throughput. So how on earth do we do that all? Obviously, I am extremely biased. I mean, I'm here today talking about the AZTEC protocol, and I believe that we have some of the solutions to these problems. And so what is AZTEC? It's a way of, obviously, transferring private value, but it's done so with some considerations in mind. Specifically, the AZTEC protocol, our zero-knowledge proofs are extraordinarily efficient to verify and validate. And that was, for us, extremely important, because obviously we are working with not just enterprise, but also with the public Ethereum blockchain, and their throughput is extremely constrained. And if your zero-knowledge proofs take a lot of computational intensity to verify, then they aren't practical at all. And so we use a kind of proving system called the Sigma protocol, which is a little bit of a kind of a red-headed stepchild of zero-knowledge cryptography, because nowadays a lot of people are talking about ZK snarks and using other kind of slightly more advanced, mathematically more proving techs. But in the context of Ethereum, Sigma protocols have an enormous amount of value, because well, I'll go into that in a little bit, but first I'll just talk about just exactly how the AZTEC protocol can perform confidential transactions. The idea is we validate this balancing relationship. We store in the AZTEC protocol value in a similar way to how Bitcoin Uxter objects work. So in an AZTEC ecosystem, you have these kind of discrete units of value called notes, like Uxters, except that the actual value of a note is encrypted. If you just look at the blockchain and see the events and the transactions, you have no idea what's inside of them. The public data that's available is the address of who owns this note, a public key associated with the note, and some metadata which can be used by a note owner to decrypt that note, which means that if I want to send somebody else an AZTEC note, I can do so. I can construct a viewing key that only they will know, and I will know, that they'll be able to recover with the metadata, and nobody else will. The private data of a note is obviously the value of the note, and these two private keys, a viewing key and a spending key. They're obviously a little bit self-explanatory. You need the spending key in order for the blockchain to actually process your transaction. You need the viewing key to decrypt it and figure out what's going on inside. And so we very explicitly wanted to separate these out, because you can obviously give those viewing keys to an auditor or regulator, somebody who needs to understand what's going on, but you don't want to be able to affect the outcome of any events. And every single AZTEC transaction at its core proves a balancing relationship. The idea is you have to prove, with the zero-knowledge proof that we've developed, that the sum of the values of the input nodes equals the sum of the values of the output nodes. Because if you know that, and if you can prove that, then you don't need to know nobody needs to know what's inside those nodes to understand that this transaction is mathematically legitimate, and there's no double spending going on. And we also, it's through this mechanic that you can also mix in public tokens. So, for example, tokens conform to the ERC20 standard. You can mix those in as well and convert those into notes, or redeem notes for tokens. And so the core of this is the AZTEC commitment function. The next couple of slides are a bit heavier on cryptography, but can I, just a show of hands, anyone here kind of familiar with zero-knowledge proofs, literate in cryptography? Well, more hands than I expected. Well, I won't go into these in much detail. Basically, the AZTEC protocol does require a trusted setup in a very similar manner to a ZK snark. So in this trusted setup phase, a private key is constructed, which is generally called the toxic waste key, and this key creates a large set of digital signatures. And these signatures correspond to integers that are tolerated in AZTEC that you can use as part of AZTEC's range proof. And then what you do inside an AZTEC proof to prove the values of your AZTEC notes are constrained within this range, all you need to do is prove that your note was created from one of these signatures, and that it was signed by the right toxic waste private key. I should add that we do have a multi-party computation ceremony planned for our trusted setup. The idea being many hundreds of people can take part, and only one of the participants has to act in good faith and destroy their part of the toxic waste for the entire protocol to be secure under conventional discrete logarithm assumptions. And so we're actually accepting signups now. So if you have any questions, if you have any concerns about our trusted setup, well, you don't have to really trust it because you can be part of it yourself, and make sure that you destroy your waste, please and thank you. But yeah, so I'll just these slides. I'm happy to go through these in questions if anybody has any particular questions about the mathematics. So these Sigma protocols that I mentioned, why are they so useful? Why are we using them instead of different kinds of proving technologies like ZK-SNUX? Well, the reason why we use them is because of their simplicity. Because in an elliptic curve crypto system, you can prove statements one of two ways. One of them is you take some kind of abstract program, and then you convert that program into a polynomial equation where you can only solve the equation if you have valid inputs to that program. And then you solve that equation expressed over an elliptic curve, and nobody can see what's going on except you. We do something different, which is we take an algebraic expression that directly reflects the mathematics that we want to validate, and we solve that expression directly in the exponent of an elliptic curve. It makes our proofs quite simple to verify and extremely simple to prove. So you can very easily construct an AZTEC proof on a hardware wallet or another very, very computationally constrained device because they're not hard at all to make. And similarly, they're extremely efficient to verify. And the reason why we think this is incredibly useful is specifically because of this last point, which sounds a little bit abstract. Different proofs can share the same common reference string. Well, why is that important? I mentioned at the start that you need a trusted setup for AZTEC to work, but you only need one trusted setup. And then you can construct a multitude of different Sigma protocols that prove different statements and different things. And you don't need any extra trusted setup. You don't need any extra mechanics in order to do that. And so the reason why this is incredibly useful for us is because this is how we are constructing customizable confidential transaction semantics in a way which still promotes asset interoperability. Because what we have at AZTEC is we don't just have one zero-knowledge proof. We actually have a family of zero-knowledge proofs that all prove slightly different things. And they use we're using these proofs to kind of compose a grammar of zero-knowledge proofs that you can then use to construct more complicated transaction semantics if you need them. For example, imagine you have some kind of digital asset where you want, for regulatory reasons, to ensure that no one person holds more than 10% of the asset. Well, you can do that with AZTEC. If you have an asset that's interest-bearing and needs to bear 3%, each AZTEC node needs to bear 3% interest every quarter, you can do that with AZTEC. And so you can have all these extra kind of restrictions or edge cases or niches, which means that you can actually, this is actually useful and can be used to construct quite custom, quite specific digital assets. For example, syndicate loan, a bond or mortgage, that's kind of the ideal we're working towards. But you can do so in a way which is still interoperable. They still share the same interface. They still share the same transfer mechanics. So if I'm building a zero-knowledge DApp, say, like a clearinghouse or an exchange, a confidential exchange, a confidential decentralized exchange, then I can still send these transfer instructions to these zero-knowledge assets and have confidence that they will work, just in exactly the way that you can do so with an ERC20 token, even though all the ERC20 tokens that exist are quite custom and have their own foibles and edge cases. So this is kind of a schematic of how it all fits together. So this is kind of summarizing what I was talking about before about the joint split transaction. If you have some ERC20 tokens, you can convert them using our commitment function into AZTEC notes. You can then construct a joint split transaction. So you basically, you prove the statement. You have some input notes, you have some output notes, you prove they match. You prove the values balance. Ideally, if you have some other AZTEC notes, you want to mix those into your transaction to muddy the transaction graph. And something else to add here, which I forgot about earlier, is notes can be worth 0, which is extremely important because that's how you add extra obfuscation and privacy. Users of AZTEC are encouraged heavily to, in every single transaction they make, construct quite a lot of zero-value notes and then use them and integrate them into their future transactions. Because in doing so, you provide even less information to any snooper or somebody trying to use statistical methods to figure out what's going on. And obviously, the notes that you're creating, they can have different owners, and that's how you transfer value. So I mentioned before this family of zero-knowledge proofs and the grammar I was talking about. How this all works is through our cryptography engine. So this is a suite of smart contracts that are currently deployed on a few test nets that enable these customizable transaction semantics, because the idea is our cryptography engine can act as the ultimate arbiter of whether a zero-knowledge proof is true or not.
And you don't need to trust us to do that, because obviously all the code is public and fully, eventually, before we go to production, will be fully audited and formally verified. And you don't need any oracles or anything like that. And if you have multiple digital assets and dApps that all listen to the same cryptography engine, then suddenly that really opens up this asset interoperability world that I was talking about. Because now, if you have some kind of confidential digital asset and it gets some instruction from a dApp some random dApp, obviously that digital asset has no knowledge of that dApp and can't trust it. But it can query the cryptography engine with the instruction it's received and gone, hey, has this come from a valid proof or not? And obviously then the cryptography engine can answer that question, and then the asset can either receive or reject the instruction it's received. And in doing so, that's how you can build up this level of interoperability. And so this is kind of the first set of proofs in our family of proofs that we're releasing in our version 1.0. So obviously the basic joint split transaction, a bilateral swap for trading. So two different assets and different asset classes, they can be traded. Dividend computation, so if you need to perform interest rate payments or some other kind of percentage-based calculation, you can do that with AZTEC. And then also these breach proofs. So if you need to just prove basic things, like for example, maybe in order to trade, you have to have over a certain threshold of value in your notes. Otherwise, you don't want to, because otherwise you'll be wasting people's time. And these are the kind of gas costs on the public Ethereum mainnet today. So you can see they are, in the context of zero-knowledge proving systems, remarkably efficient. 800,000 gas for a basic transfer. And this will only decrease substantially with planned protocol upgrades by about a factor of 5. And so we hope that this kind of this very high efficiency will really help with throughput, because anyway, I can go to that a little bit later. So this is all culminated in the ZK, what we're calling at the moment ZK ERC20, a confidential token standard for Ethereum. It has a very similar interface to an ERC20 token, so people will hopefully be familiar with it. And if you construct a confidential digital asset according to this, that follows this interface, then you'll be compatible with all the other tokens that also use the AZTEC protocol and any zero-knowledge confidential dApps that are constructed. And so you can use, and then again, this is just highlighting what I was talking about before, the fact that you can have these customizable transaction semantics, but still in a manner which is still largely interoperable with other confidential assets. So we're trying to enable this ecosystem of zero-knowledge dApps, because this massively, massively cuts down on the kind of computational burden of performing these kind of transactions. Imagine if I'm running a confidential exchange, and my confidential exchange takes confidential orders, and it has its own zero-knowledge proof to validate that these orders match the semantics that I care about, that the buyer and the seller, their prices are matched, and that everybody is okay with this transaction proceeding. My smart contracts are going to talk to these zero-knowledge confidential assets and tell them to do something. Hey, this person wants to trade, destroy these notes, make these notes in their place. But these dApps don't have any knowledge of the exchange. They aren't going to just listen to those instructions. They have to then query the cryptography engine. But here's the thing. That trading proof I mentioned earlier, it already proves the balancing relationships required for these zero-knowledge assets to perform their transfer. And so really, if these zero-knowledge assets have to then validate their own zero-knowledge proof, that's just extra redundant computation, wasted computation. And so if they're all listening to the same cryptography engine, that cryptography engine can validate the legitimacy of those instructions without having to validate additional zero-knowledge proofs. And so in this example, it cuts the gas costs down by 1/3. And so you have a confidential trading mechanic, which normally would have a gas cost which will blow through the block gas limit of Ethereum, reduces down to about 800,000 gas. Which is eminently achievable and practical for a large range of applications today. And so this is crystallizes the two Ethereum improvement proposals we put forward, EIP 1723 and 1724 for our cryptography engine and the confidential token, respectively. And so finally, last slide. This is all kind of the latest, the cold face of what we're currently researching and working on is in our AZTEC monorepo, where we're kind of focusing very heavily on providing high quality tooling and interfaces that are needed for this technology to be workable. So those are the two packages where most of the mechanics happen. And if you're a developer yourself and want to have a look at this, please feel free to check it out. It's all licensed under the LGPL. So yeah, sorry, that was actually a penultimate slide. This is our roadmap. So this is actually what we're doing. So this isn't just some kind of like high like high-tech theoretical fiction that I'm talking about, some kind of imagined future that could possibly exist. This isn't actually working today. It's actually been working since November, which is when we created a confidential representation of DAI, the dollar stablecoin, and started trading around these zero-knowledge notes within the office. So Q1 this year, we're going to be releasing like the full cryptography engine with its family of zero-knowledge proofs and deployed to testnets, as well as our full complete proof construction API. So currently we have 3 proofs in our library. Imminently planning on extending that to the 5 I mentioned before, as well as kind of this optimized elliptic curve arithmetic contract, which will cut the gas costs of what we're doing down by a little bit. And then in Q2, we'll be finishing our trusted setup multi-party computation. So we really want to get this right the first time, and we're involving as many people from the Ethereum community as we can get our hands on. So please, if you want to be involved yourself, just either talk to me or email hello@aztecprotocol.com. So at the moment, if you want to kind of tinker around and get a feel for how AZTEC works, the trusted setup that we have was one that I ran locally just as just for development purposes. And so if you want to kind of get going in AZTEC and start building confidential assets, you can use that. But obviously, our production grade libraries will be using the multi-party computation trusted setup, which will be obviously much more secure than something I just ran locally on my laptop. We'll also be formally verifying our smart contracts because obviously this is bespoke, custom-grade zero-knowledge cryptography. If there was ever a need and a use case for formal verification, this would be it. We've already formally proved that the mathematics behind our zero-knowledge proofs are sound. You can't fake a proof. But we also want to prove that our smart contract code is a direct expression of these mathematics. And then finally, in Q3, we'll be releasing our production-grade cryptography engine and suite of libraries, and then focusing very heavily on providing the tools for wallet integrations and other AZTEC integrations that we can think of. So thank you very much for listening. That's been the AZTEC protocol. Happy to answer any questions anyone has.
A couple of questions. Is it working? Sorry, just on mine. Are you working with any particular Ethereum clients? So do you have to sort of integrate with each one, or is it a standard thing?
So it's we don't have to work with any Ethereum clients. It works on top of the basic Ethereum protocol. We don't need any extra special precompiled contracts. We do use precompiled contracts, but they're the ones that were included in the base Ethereum specification. I think in the Metropolis hard fork last year in 2017. Yeah, that's the only kind of prerequisites that are required for our protocol to work.
Okay. And second question is, I've seen talk of something called Starks,
yes,
which claim to not require a trusted setup.
Yes.
So is this something you've looked at, and is it?
Yeah, absolutely. I wish I could just kind of hide off on an island somewhere and spend a month reading about Starks. They're fantastic, amazing piece of technology. The reason why we don't use Starks is because Starks are quite computationally expensive. It's very computationally expensive to verify Stark proofs, and the proof sizes are very large. So a lot of zero-knowledge proving technologies, if you listen to some talks and presentations made by other zero-knowledge proving technologies, there's a very heavy focus on the validating batches of transactions, and there's a very good reason for this. The computational cost of validating a zero-knowledge proof can be extremely high, but if you validate an enormous number of proofs at once, then the marginal extra cost of validating a single extra proof is very, very low. And so, for example, if you want to validate 10,000 or 20,000 confidential transactions at once, then a ZK Stark is extremely practical and useful, because the amount of time you need to validate a proof scales with the logarithm of the number of proofs you have. However, that comes at a huge cost, and that cost is generality, because you can only validate 10,000 or 20,000 zero-knowledge proofs at once if those proofs all conform to exactly the same semantics. What we were focusing on at AZTEC was creating a zero-knowledge proving system where it's extremely efficient to validate a single zero-knowledge proof. And for now, to not particularly worry about scaling. We aren't a scaling solution for Ethereum. However, what we can do is provide these kind of highly tailored custom proofs that don't cost them very much to validate individually, and that means that each individual proof can be a little bit different, and you can have these kind of customizable assets, which is why we're focusing on like the Sigma protocol-based approach.
The cryptography engine, is that on-chain or off-chain?
So the cryptography engine is on-chain. It's just a suite of smart contracts they're currently in a monorepo, and so they're just like an on-chain program that validates these zero-knowledge proofs. They don't require any off-chain like help or assistance or oracles.
Okay, thanks.
I think you had a slide on there that said that the proof construction library was JavaScript.
Yes.
Is that right? Yeah, I mean that's you weren't tempted to. I think the existing stuff's in C++ and sort of very.
Yeah. So obviously, when you're thinking, I'm going to make a cryptography library, what language am I going to choose? JavaScript.
That's the question. Really.
Not really intuitive. No, my background is in C++ actually, but we chose JavaScript for a reason, and the library is in JavaScript just because the vast majority of applications on Ethereum are web-based, and having a web-based, web-compatible library is just much easier for user adoption. So we do actually have some we also have like a C++ and a WebAssembly version of our cryptography stuff, but the focus at the moment has been on the JavaScript library for that reason.
Very good.
So you mentioned in quarter 2 you're going to be looking at formal verification.
Yeah.
Are you going to be using tools which are already available, or are you going to build your own?
I'd really rather not build my build our own. Very interested in what's happening, like what's been the tooling that's being built around the K framework. I believe there has already been quite a few spot contracts that have been formally validated by MakerDAO using that framework, and so we very much want to like kind of iterate and build on what they're working on at the moment.
Last question. Yeah.
Just thinking back to some of the other talks, how do you get finality then if your cryptography engine is online?
So obviously, because we're a smart contract protocol built on top of the Ethereum protocol, we piggyback off the finality of any of the underlying blockchain protocol that's being used. So obviously, for the public Ethereum blockchain, we piggyback off their finality time. And so obviously, latency is between it can be up to like 2 hours. But if you're using a POA blockchain version of Ethereum, then finality is basically whatever you want it to be.
Okay.
Okay, thanks for the presentation. Really good. I think